In today's video, we're going to look at inverse functions, and given a function, can we find its inverse, and also look at evaluating inverse functions at a particular point. The first thing I want to look at is what functions actually have an inverse, and how can we tell from the graph that we can actually get an inverse from a function. So we already know that the definition of a function means that it must satisfy the vertical line test. So the classic example that we always use is that if the graph of a function was this, it obviously can't be a function because it does not satisfy the vertical line test. For each x value, you don't have a unique y value. So some x values have two separate y values, hence this is not the graph of a function. So we know that to be a function, it must satisfy the vertical line test. In order for a function to have an inverse, we actually say it must also satisfy the horizontal line test. So, for example, if I were to take the graph of a quadratic, so a standard y is equal to x squared graph, yes, we know it's a function because it satisfies the vertical line test. For each x value, there is only one y value, but it actually does not have an inverse because it does not satisfy the horizontal line test. In order to have an inverse, every y value must also have a unique x value. So we also have the opposite being true in order for a function to have an inverse. So let's write that down. In order to have an inverse, a function must have a unique x value for every y value. So the opposite is also true in the case of a function having an inverse. So that means that in order to be a function, we know it must satisfy that vertical line test. So for every x value, there is a unique y value, but also in order for a function to have an inverse, to find the inverse of a function, we know that it always has to satisfy this horizontal line test, meaning there is a unique x value for every y value. So every y value only has one x value. This actually means that the function is 1 to 1, okay? Because both of these have to be satisfied. In order for it to be a function in the first place, it has to have one y value for every x value, and for the horizontal line test to have that inverse, we know that it has to have one x value for every y value. So that tells me that there must be a unique x value and unique y values, okay? So there is only one y value for every x value and only one x value for every y value. So it is 1 to 1, okay? Another way to tell if a function has an inverse is actually by looking at it algebraically. A function will have an inverse if you can find this function g such that that combination f of g of x equals g of f of x. Now this will not be the case for every function g for a given f function, okay? So if I have f of x, I will have to find that specific function g of x, that specific inverse, and then this will be true. So if you find that f of g of x is equal to g of f of x, that tells me that f and g are inverses of one another. Like I said, it won't be the case for every single function g of x for a given f of x, meaning that f of x has an inverse. You will have to find that specific g of x for which this is the case, And then that tells me that f has this inverse g of x. So if you find for a particular g of x function, that f of g of x is equal to g of f of x, then this must mean that g of x is the inverse of f of x. Okay, and vice versa. Okay, f of x is also the inverse of g of x. They are inverses of one another. So the way that we write that is to say that the inverse of f of x is g of x, and similarly the inverse of g of x is f of x. So that's how we actually write inverse functions. Do not write 1 over f of x. That is not the inverse. It's f to the power of -1 of x. Let's look at some functions that may have an inverse, okay? My first example is going to be the function f of x is equal to x squared plus 6. Okay? Does this function have an inverse? Well, if we take it back to what I was doing with graphs, if we were to graph out x squared plus 6, you would have this quadratic. It will have been shifted up by 6 units, but it is a quadratic graph. And we've already said that a quadratic does not satisfy the horizontal line test, because in order to have an inverse, the function must be 1 to 1. I must have a unique x value for every y value and a unique y value for every x value. So this particular function we already know doesn't satisfy the horizontal line test, which must mean it doesn't have an inverse, because it is not 1 to 1. Another quick example that I will do is f of x is equal to 4x cubed. This is 1 to 1 over its whole domain, so between -infinity to infinity, whichever x value I pick, I know that I have a unique y value, and similarly for a y value, I've got that unique x value. So because this is 1 to 1 and satisfies that horizontal line test from the graph, I know that it must have an inverse. Let's look at evaluating some of these inverse functions. Okay. If I have a function f of x and it has an inverse, we'll call it f inverse of x. Okay. If I've got a particular point, we'll call it a, b, and it lies on the graph of f of x, for the inverse function, you actually find that by switching the x and y coordinates, that point will then lie on the graph of the inverse function. Okay, so if I have the point 1, 2, okay, so 1 is my x coordinate, 2 is my y coordinate, and that lies on the graph of f of x, then that tells me that the point 2, 1 will lie on the graph of f inverse. So you just switch the x and y coordinates, and then that particular point will lie on the graph of the inverse function. Okay, so it just switches the x and y values. So let's say I have been given this table for a function where I've evaluated f of x at these particular points. So I've got x is 1, 2, 3, and 4. And then the function values at those particular x values are 2, 4, 6, and 8. If I'm asked to find f at 4, okay, so we are evaluating our function at the point x is equal to 4, I can see from my table that that equals 8. But what happens if I'm asked for f inverse of 4? Okay, I go to where f of x is equal to 4 and I find the particular x value. Remember, what we do here is we have switched the x and y values. Okay, so if the point AB lies on f of x, then BA is going to lie on f inverse. Okay, so f inverse of 4, okay, I go to where f of x equals 4 and find x. Because all I have done, I'm effectively switching my domain and range. Okay, so if I've got these x values are in my domain of f of x, then these values are in my range of f of x. But by switching the x's and the y's round, that means that these function values now become my domain of f inverse, and these values, these x values, are now in my range of f inverse. So that tells me that f inverse of 4, I go to where f of x is equal to 4 and I find the x value. So f inverse of 4 equals 2. Okay. Similarly, what I could do is I can look at f inverse of 2. Okay, I go to where f of x is equal to 2 and I find the x value, which would be 1. Okay, so you are just switching your domain and your range. Given this information, can we sketch the graph of the inverse of a function given the original graph of f of x? So if I've got the graph of f of x, can I find the graph of f inverse? How do I do that? Well, if we go back to what we just said, if a point AB lies on the graph of f of x, then we know that BA lies on the graph of f inverse. So by flipping the coordinates to get the points that are on f inverse, it's the same as reflecting the points that lie on f of x in the line y is equal to x. So if I've got the point AB that lies on the graph of f of x, therefore means that I switch the coordinates around, so x and y switch, and those points are on the graph of f inverse x. That tells me that to find the graph of f inverse, I take my graph of f of x and I'm going to reflect it and find the mirror image of the graph of f of x in that line y is equal to x. And so you're going to take that entire graph and reflect it across that line. Okay? So reflect graph of f of x and the line y is equal to x. So you just treat that line as a mirror. Let's look at a quick example of this. Okay. Let's say that this was my particular graph of f of x. If I quickly dot out the line y is equal to x, okay, then I reflect that whole line like that, and then this would be the graph of f inverse x, because all I have done is I've switched my x and y coordinates, so I just flip that graph in that particular line. The last thing we need to know is, given the formula for f of x, can we find the formula for f inverse x? So now we are looking at the algebra of this. Okay. So if I'm given what f of x is, can I find f inverse? Okay. Simply what you do here is, again, remember, if I've got the point A, B lies on f of x, that means that if I switch the x and y coordinates, that point B, A will be on the inverse of f. Okay? So in order to find the formula for f inverse, the first thing I'm going to do is I'm going to switch places of x and y in f of x. So if I've got f of x is equal to something, I'm going to say y is equal to that thing, and then I'm going to switch the places of x and y. So everywhere I see a y, I'm going to put x. Everywhere I see an x, I'm going to put y. The next thing you're going to do is then rearrange and solve for y. And then that tells me whatever you get for y is the inverse of x. Let's do some examples of this. First one I'm going to do is to find f inverse when I have f of x equal to the square root of 4x minus 6. Okay. So I write y is equal to my particular function. I then switch x and y. So everywhere I see a y, I put x, and everywhere I see an x, I put y. My next step is to try to solve for y. Okay, so I now want to rearrange this to get y is equal to something. So if I square both sides, I get that. Then I'm going to add 6 to both sides to get that. And finally I'm going to divide through by 4 to give me y is equal to 1 over 4 x squared, plus it would be 6 over 4, which is the same as 3 over 2. So that tells me that this particular function that I now have is the inverse of my original function f of x. Okay. Try another quick example. So let's say we're trying to find f inverse for f of x is equal to 1 over 2x minus 3. Okay. Again, I write y is equal to what I have for my function. Everywhere I see a y, I put an x, and everywhere I see an x, I put a y. Now I need to solve this for y. So I'm going to multiply both sides through by 2y minus 3. And I'm going to divide both sides through by x. I'm going to add 3 to both sides. And then when I divide both sides through by 2 at this point, you can divide both terms here through by 2. So I would get 1 over 2x plus 3 over 2. That's totally fine. I'm actually going to make this into one fraction. So I'll let you go ahead and do this. But it actually simplifies to that. Okay, so I've put this all as one fraction. The last thing that I want to quickly discuss on my last example is looking at this domain and range. Remember, we said that the domain of f of x is equal to the range of f inverse, and the range of f of x is equal to the domain of f inverse. So the domain of f of x is equal to the range and the range of f of x is equal to the domain of f inverse. Okay. This is because we said that if you've got a particular point on f of x, you just switch the x and y coordinates, therefore you're switching the domain and range when you do this. So this time, for this example, I'm going to find the inverse of f of x is equal to 2x squared minus 1 on the restricted domain x is greater than or equal to 0. There's another reason we have done this. Remember, this is a quadratic, meaning that a normal quadratic is not 1 to 1, which means that we can't find an inverse. But by restricting its domain, if we looked at the graph of this, it is now 1 to 1 because we are saying that x can only be greater than or equal to 0, giving me the right-hand side of that graph. I completely get rid of the left-hand side, and that makes it 1 to 1. So again, we're going to try and find the inverse of this. So y is equal to 2x squared minus 1. I switch x and y. And now I'm going to solve for y. Okay. You see the issue here normally when trying to find the inverse of this function. Okay. I end up with two values of f inverse for every single one of my x values. I get a positive and a negative. So that's the issue. But remember, we have restricted our domain of f of x. So my domain of f of x equals my range of f inverse. So if I've restricted my domain as x is greater than or equal to 0 for f of x, that tells me that the function value that I get out of f inverse, my range of f inverse, must also be greater than or equal to 0. So because I know that f inverse of x has to be greater than or equal to 0, my range has to also be any positive number. It tells me now that I do not have to consider the negative part of that particular function. Okay, I don't have to worry about this negative here because I know that my range is 0 to infinity. So my domain and range of f inverse in this case, we can determine both of these. We know that the range of f inverse has to be the same as my domain of f of x, which we said was x is greater than or equal to 0, so my range is from 0 up to infinity. My domain of f inverse of x, let's go back and look at my function. It would be the same as the range of this particular function, but we can get it from looking at f inverse. My domain of this, remember, I cannot square root a negative number. So I can only square root this if the number under that square root is 0 or greater, meaning that my domain is -1 up to infinity, because if x is anything less than -1, it makes the number under the square root negative, which I can't square root. So my domain of f inverse is -1 up to infinity. Like I said, you can either get that from looking at the range of your original function or by looking at your function f inverse and then determining what that domain could be. If you draw a quick graph of this and sketch a quick graph, your original function f of x would look something like this. If you then dot out what that function what that y is equal to x line would look like, and then we can go ahead and draw a quick sketch of what f inverse would be. And you can figure out x and y intercepts, etc. This is just a very quick sketch. But this is how you would determine, number one, what the function is, number two, that domain and range, and three, a quick sketch of the graph.